All right, welcome back to our explainer on set theory. Last time, we started putting together our logic toolkit with negation and conjunction. Today, we're going to add the final three essential tools and round out the set. So, let's jump right in with a problem that comes up all the time in everyday language: ambiguity. Imagine someone tells you, I'm going to get a master's degree or a PhD. What do they actually mean? Could they get a master's? Sure. A PhD? Yep. But what about both? In normal conversation, it's kind of fuzzy, right? But here's the thing. The world of formal logic, which is the bedrock of all of mathematics and computer science, simply can't operate with that kind of fuzziness. It demands absolute, rock-solid precision. So how does logic get around this problem? Well, let's find out. Our first new tool is designed to solve that OR problem once and for all. It's called disjunction, and it gives us a perfectly precise mathematical way to handle these situations. The symbol we use for this looks kind of like a V. You just place it between two statements, P and Q, and you read it as P or Q. Simple enough. But, and this is the crucial part, in logic, this is defined as the inclusive OR. And what that means? Well, it makes all the difference, as you're about to see. And here we go. This truth table clears everything up. Just look at that first row. If P, getting a master's, is true, and Q, getting a PhD, is also true, the whole P or Q statement is still considered true. So boom, there's our answer. In the language of logic, the speaker can absolutely get both degrees. The only way for the statement to be false is if they get neither of them. All that ambiguity, it's just gone. All right, next up is a tool that is a really big deal. It forms the backbone of countless mathematical theorems and logical arguments. We're talking about the conditional, better known as the if-then statement. The symbol for the conditional is this arrow, and we read it as if P then Q. Now, the best way to think about this is like a contract or a promise. It's basically saying if the first part is true, then the second part is obligated to be true. Now, this truth table, it has a weird little quirk that trips people up at first. As you can see, the only time a conditional statement is considered false is in case 2. That's when the premise P is true, but the conclusion Q turns out to be false. You can think of this as a broken promise. That's it. That's the only time it's false. So you're probably wondering, wait a minute, why is it true when the first part is false? Let's use the example from our source text. I promise you, if it is raining, I will give you a ride, okay? Now, what if it doesn't rain? Did I break my promise? Of course not. The initial condition, the rain, never happened, so my promise is still totally intact. It doesn't matter if I gave you a ride or not. The contract wasn't wimpin'. And this isn't just some random choice. The book confirms this is a formal agreement, a convention that logicians settled on. Why? Because defining it this way makes the entire system of logic powerful and consistent. It allows for elegant proofs of really useful theorems that would be super awkward or difficult to prove otherwise. Okay, on to our final tool for the day, the biconditional. Now, if the conditional was a one-way street, you can think of this one as a two-way street. It's all about logical equivalence. This one is seriously powerful. It's essentially two conditional promises rolled into one. It's saying if P's true, then Q must be true. And if Q is true, then P must be true. They are logically locked together. And the truth table makes this crystal clear. The only times the statement as a whole is true are when P and Q are perfectly in sync. They're either both true together or they're both false together. If one is true and the other is false, nope, the lock is broken. So let's nail this down. The conditional is your one-way street. The truth of P forces the truth of Q, but not necessarily the other way around. The biconditional, however, that's the two-way street. They rise and fall together. That signifies a true logical equivalence. And just like that, our foundational logic toolkit is complete. With these 5 tools, we can finally start building and analyzing much more complex arguments. So let's do a quick review of the complete set. We started our journey with negation and conjunction. Today, we added the inclusive OR of disjunction, the if-then promise of the conditional, and the two-way street of the biconditional. These 5 operators, they are the fundamental building blocks for constructing pretty much any formal logical statement you can think of. But why does any of this really matter? As our source material points out so well, this isn't just about abstract symbols. The most important job of a mathematician or a scientist is to be a kind of translator. It's about taking a vague, intuitive idea and turning it into a precise, testable proposition. And these tools, this is the language you use for that translation. This is the language that builds proofs, that writes computer programs, that deepens our understanding of the universe. It empowers you to take an idea and make it provable. So now that you have all the tools, the only question left is, what idea are you going to translate first?